Hello everyone and welcome to Sky Scholar. In our last video I decided to clarify some of the issues related to the Sun. I stand by my position as outlined in this response. Gaseous stars cannot exist as they violate the laws of thermodynamics. Gases don't spontaneously self-compress in thermodynamics, as it takes an external agent to work on a system in order to decrease its entropy or raise its temperature. By advancing the self-compression of a gas, astronomers have dispensed with the need for this agent and have therefore moved outside the confines of the laws of physics. They do so by inappropriately invoking the Virial theorem, as I highlighted in this video, and thereby obtain a non-intensive temperature for the stars, which is a violation of the zeroth law. They believe that every large cloud of matter in the universe is just sitting there, ready to gravitationally collapse. However, kinetic theory fully describes the energy distribution of an ideal gas, and when one adds potential energy to such a system, one can no longer utilize conclusions from kinetic theory. You get nonsense. Furthermore, kinetic theory requires the presence of a real surface in order to have pressure. In arguing otherwise, the astronomers are simply ignoring those aspects of kinetic theory which call into question their implausible claims. Beyond their gravitational collapse of a gas, the astronomers have long inappropriately set a temperature of the photosphere at approximately 6,000 Kelvin. In setting this temperature, they have failed to realize that it was not real. They are being fooled by the sun. In this regard, most people recognize that the temperature of the Sun was always determined using its thermal spectrum. The problem is that this method does not tell the whole story. It is true that the solar spectrum at first sight seems to follow the laws of emission, yet in their quest for advancement, the astronomers have failed to take into account the simplest aspects of these laws. I have described the laws of emissions in these two videos, and if you have not seen them, please have a look. For today's video, remember what Stefan's law states, namely that thermal emission in a blackbody must increase with the fourth power of the temperature. If the temperature of a blackbody goes up, its emission moves up dramatically. Unfortunately, this never happens in real gases and plasmas. Now let's see why that is. First, the most important feature of setting a temperature using thermal spectra is that one must have a complete understanding of the energy distribution of the source. Namely, all the energy must be contained in degrees of freedom which are vibrational in nature. The sample must not have access to convection or conduction. Graphite and soot on Earth come closest to meeting this requirement, as most of the energy which enters such a system does so through the vibrational lattice. In graphite, we have a single type of bond, the carbon-carbon bond, in the hexagonal planar lattice. So in a real blackbody, one sees a single type of bond, or at least bonds that have very similar bond strengths. A real blackbody cannot have access to multiple vibrational degrees of freedom, which differ vastly in their ability to handle energy. If this happens from a thermodynamic point of view, one risks having two separate uncoupled systems in the same body. This, in fact, is what happens in water, and we will return to that later. In any case, objects which have convection currents are not at thermal equilibrium by definition. That is why their thermal spectrum must be treated with extreme caution. The Sun clearly has access to convection currents, as anyone can note in this video on solar granulation. Moreover, the Sun has internal convection currents, as can be seen here. It is also subject to differential rotation at the level of the photosphere. It is these convection currents which compromise the ability to set a proper photospheric temperature on the Sun. Here is how Max Planck cautioned about thermal equilibrium. Now, the condition of thermodynamic equilibrium requires that the temperature shall be everywhere the same and shall not vary with time, for the heat of a body depends only on the heat radiation, since on account of the uniformity in temperature, no conduction of heat takes place. Planck understood that the presence of conduction could compromise all attempts to have thermal equilibrium. He did not even bother addressing convection, because any object displaying convection is clearly not in equilibrium. The Sun has powerful convection currents, so it is not in thermal equilibrium. As such, the astronomers should have been more cautious. Convection is not a subtle process. Here is what Max Planck said about setting the temperature of the Sun from its thermal spectrum. Now, the apparent temperature of the Sun is obviously nothing but the temperature of the solar rays, depending entirely on the nature of the rays, and hence a property of the rays and not a property of the Sun itself. Therefore, it would be not only more convenient, but also more correct to apply this notation directly, instead of speaking of a fictitious temperature of the Sun, which can be made to have meaning only by the introduction of an assumption that does not hold in reality. More than 100 years ago, Planck cautioned the astronomers that their temperature of the Sun was not valid. Yet no one paid attention to Planck. Now I am simply restating the objection, but I am supplementing the argument with the underlying reasoning. One cannot set a proper temperature to a thermal spectrum originating from a source which has access either to conduction or convection. Now, in order to build on these ideas a little, let's also discuss a concept typically learned in advanced chemistry or physics classes on statistical thermodynamics, namely energy partition. When we discuss energy partition, we are dealing with how the energy distributes itself within the thermodynamic system. In order to understand how energy partition works, let's begin with a simple monoatomic gas like helium. If you try to place energy into a helium system, the gas responds by placing the energy into its translational degrees of freedom. Each atom can move in the x, y, or z direction, and the velocity of motion can be made to increase. Equipartition states that the energy contained in each of these possible 3 degrees of freedom must be equal. We can use 3 containers to represent these 3 degrees of freedom. Again, equipartition states that we have to place equal amounts of energy in each container. Helium gas provides a simplified analysis, as it has access only to translational degrees of freedom. Next, consider a heteronuclear gas like hydrogen chloride. Hydrogen chloride actually has access to 7 degrees of freedom. Again, there are 3 translational degrees of freedom along x, y, and z, but now there are also 2 rotational degrees of freedom. The rotations occur about the directions perpendicular to the bonding axis. Finally, the hydrogen chloride molecule can vibrate about its bond and place some of the energy into its vibrational degrees of freedom. One might think that the molecule should have only 6 degrees of freedom, since there is actually only one vibrational mode, and often that is what is taught. But actually, it is a little more complicated. For each vibrational mode, there are actually 2 quadratic variables involved, and hence 2 degrees of freedom, as described in this text. Those details are not important, but you can learn about it if you wish. In any case, once again, equipartition states that an equal amount of energy must be placed in each of these degrees of freedom. More complex multiatomic gases will have access to even more degrees of freedom, and equal amounts of energy can enter each. There are restrictions to this which arise from quantum mechanics. Sometimes modes can be frozen out, for instance because temperatures are too low to activate a vibrational degree of freedom. But as a rule, equipartition holds impressively well once all the modes can be accessed in a gas. Now let's consider what happens in hydrogen chloride gas. The 3 translational degrees of freedom do not contribute to the total thermal emission. But since hydrogen chloride has a dipole moment, the rotational degrees of freedom combine with the vibrational degrees of freedom and cause the gas to be able to absorb energy in vibrational rotational bands. This absorption requires quantum mechanics to explain. Now, what about the emission in a gas? As a result of having access to the translational degrees of freedom, when a gas is heated, its total emission goes down, not up, contrary to the laws of thermal emission. Here is an example of the emission from carbon dioxide for various path lengths as a function of temperature. There is another problem, namely that there is only so much energy that can be placed in the vibrational degrees of freedom in a gas. Otherwise, the bonds break and the diatomic or multiatomic gas no longer exists. It is for such simple reasons that gases can never act as blackbodies, and why a gaseous sun can never produce a blackbody spectrum. Gases cannot follow the laws of emission. They have access to convection as they populate their translational degrees of freedom. In addition, gases and gaseous plasmas lack access to an extended vibrational lattice required to produce the continuous spectrum. That is why they emit primarily in vibrational rotational bands, although gaseous plasmas can also have access to non-Planckian continuous emission due to electron capture. Now, why did I use hydrogen chloride as an example and not just molecular hydrogen gas? It is because hydrogen chloride has a dipole moment, and as such, it can exhibit a vibrational rotational spectrum. Conversely, molecular hydrogen gas does not possess a net dipole moment and cannot exhibit such a spectrum. Hydrogen only has access to electronic emissions. In any event, the gaseous plasma model of the Sun will never be able to properly account for the blackbody spectrum due to the presence of translational degrees of freedom and the lack of a structural lattice. That being said, what happens in a liquid sun? I addressed this previously in this paper. Once again, we have access to translational degrees of freedom, as convection clearly exists on the surface of the Sun. Let's place all that energy in one big pot. In addition, we have access to vibrational degrees of freedom because the Sun is actually comprised of condensed matter. We place that energy in another pot. Now notice how I made the pot for the vibrational degrees of freedom much smaller, and I place much less energy in that pot. I have previously stated that the photosphere has a real temperature in the millions of degrees. Why did I say that? Why not place equivalent amounts of energy in translation as in vibration on the Sun, just like was required with equipartition? The answer comes in the realization that in order for equal amounts of energy to be placed in each degree of freedom, the system must be capable of complete interaction between the degrees of freedom. This does not appear to happen in the Sun. Rather, it appears that huge amounts of energy are trapped in convection currents, which is unable to couple to the hexagonal planar lattice. It takes a great deal of energy to drive those currents. In fact, I postulate that it takes much more energy than found in the vibrational degrees of freedom associated with the hexagonal planar lattice. But now, how can one get a handle of how much energy is contained in convection currents? Well, the simplest answer is to examine what happens during a solar flare. When the flare breaks the surface of the Sun, an enormous amount of X-rays can be produced. Those X-rays are being generated through the collision of two masses. First, the flare itself moving orthogonal to the surface of the Sun, and second, the photospheric material moving parallel to it. That implies that the energy associated with the translation of these materials is equivalent to a temperature of millions of degrees. That is how one can gather that the energy associated with convection currents is so massive. Within the Sun, we also have access to conduction. Electrons are flowing in conduction bands, but that amount of energy remains difficult to ascertain. However, we see its effects, as magnetic fields are clearly being generated throughout the solar surface. In any event, equipartition does not hold in the stars. The energy in the translational degrees of freedom is essentially completely uncoupled from the energy contained within the vibrational lattice. You can think about it this way. Take a piece of graphite in space and impart some translational motion to it. If you greatly increase the translational motion, you will not affect the temperature of the graphite. It will have more kinetic energy, but that kinetic energy is completely uncoupled from the vibrations associated with its temperature and its thermal emission. The same dissociation between translational degrees of freedom and the vibrational degrees of freedom exists on the Sun. That is how a lattice occurs in the presence of powerful convection currents. The atoms that comprise the lattice all have the same amount of translational energy. and they thereby get to form an extended structure, just as if there was no translation present at all. In the end, when we are sampling the thermal spectrum of the Sun, we are not sampling the total energy content of the photosphere. Rather, we are sampling the energy in the degrees of freedom associated with the lattice producing that spectrum. The Sun has a true lattice, and its thermal spectrum is the surest proof. The solar spectrum is giving us a glimpse at the vibrational degrees of freedom, but reveals nothing about the energy associated with convection. Still, because a lattice exists, the photons released can excite atoms just above the photosphere. That is why those atoms also report a temperature which agrees with the extracted temperature from the solar spectrum. In any case, the distribution of energy in stars is much more complicated than imagined at first glance. Planck was correct. The thermal spectrum of the Sun does not properly report the energy content of the photosphere, and this is for two reasons. First, because we do not have thermal equilibrium as convection currents exist, and second, because the translational and vibrational degrees of freedom on the Sun are uncoupled from one another. Equipartition does not hold in the Sun. Well, that is all for now. If you enjoyed the video today, promote the channel. Mention the videos to your friends and your local astronomy club. Support me with a like and subscribe for more videos as we look more closely at the Sun, the stars, and beyond. Comments are always welcome down below, and I'll see you soon on our next video.